Okay, hello everybody. I hope this works. Let's recall that some time ago we proved the Hahn-Banach theorem, which roughly states that if we have a normed space and a bounded linear functional defined on a vector subspace of this space, then we can always extend this functional to the whole space in such a way that the extension will be also a bounded functional and such that it has the same norm as the original functional. Well, actually, this is not exactly the Hahn-Banach theorem, but rather this is probably the most important corollary of the Hahn-Banach theorem. Our first goal for today is to discuss some nice corollaries of the Hahn-Banach theorem, which are stated in terms of annihilators and preannihilators. Okay, so suppose that we have a normed space, X, and we give the following definition. We define the annihilator of a subset M in X to be the following subset of the dual, which is denoted like this. So this is a set consisting of those linear functionals on X, such that F vanishes at M. That is, the following condition holds. So this is a subset in the dual. And dually, we define the preannihilator of a subset N of the dual to be a subset of X, which is denoted like this. And it consists of those elements in X for which the following condition holds. Each linear functional F in N vanishes at X. So this is a subset in X. The Russian for annihilator is Annihilator. The preannihilator is Preonulators. Okay, so let's to begin with, let's observe that in the case of a Hilbert space, this is our observation 1. If H is a Hilbert space, then annihilators and preannihilators are closely related to orthogonal complements. Namely, we have a canonical bijection R between H and H star. This is a canonical bijection. From the Riesz representation theorem. And if we look at the definition of the annihilator, we can easily see that for each subset of H, for each M in H, the annihilator of H, the annihilator of M, is nothing but the canonical image of the orthogonal complement. Of M. This is immediate from the definition of the annihilator and from the explicit form of the canonical bijection. So let's recall, just in case, that the canonical bijection takes each element x to the linear functional fx given as the inner product with x. So this bijection takes the orthogonal complement exactly onto the annihilator. And similarly, for each subset M in the dual space, the preannulator of M, of N, is nothing but the orthogonal complement of the pre-image of N. So this observation explains why annihilators and preannulators are denoted in the same way as orthogonal complements. Well, there are some questions in the chat. Okay. Fine. In the general case, here's one more observation. In the general case, we have the following relation between annihilators and preannulators. So if X is any normed space, we have the canonical embedding Ix of X into the bidual which takes each element in X to the evaluation functional. And let's observe then that for each, well, first of all, for convenience, let's, since this is an isometric embedding, let's identify X with the canonical image of X in the bidual. This is convenient. To identify X with its image in the bidual. And then, for each subset N in the dual, we have the following equality. The preannihilator of N is the intersection of the annihilator of N with X. Again, this readily follows from the definition and from the explicit form of this canonical embedding. In particular, we see that if X is reflexive, that is, if this is a bijection, in particular, if X is reflexive, then the annihilator and the preannihilator of N are the same. So in this case, the annihilators and preannihilators are essentially equivalent objects. Let's now look at some simple properties of annihilators and preannihilators. So we have the following proposition. Proposition 1. First of all, for each subset M in X, the annihilator of M is not just a set, but this is a closed vector subspace. Is a closed vector subspace. of x star of the dual. Well, actually, this is almost immediate from the definition. If we look at the, once again, at the definition of the annihilator, we see that, what is this? This is just the intersection well, anyway, I tried to say that this is the intersection of the kernels. This is not exactly the case because we can interpret this as follows. For each x, we can consider the respective evaluation functional, epsilon x on x star. And then this is just the intersection of the kernels of the respective evaluation functionals. But the kernel of a functional, of a bounded linear functional, is a closed vector subspace. And for the same reason, the preannulator of any subset in the dual is a closed vector subspace of x, because this is just the intersection of the kernels of functionals from n. And the intersection of closed sets is also closed. So, and this is property 2. For each subset n in x star, the preannulator of n is a closed vector subspace. Of x. Property 3 is also very easy. So if we take again an arbitrary subset in x, then the following equality holds. If we take the closure of the linear span of M, then the annihilator of this subspace is exactly the same as the annihilator of M. And this also easily follows from the definition, because if a linear functional vanishes on M, that is, it belongs to this annihilator, then automatically, by linearity and continuity, it vanishes on the closure of the linear span. So we have this equality. And essentially, for the same reason, for each subset n in x star, the preannihilator of n is the same as the preannihilator of the closure of the linear span of n. Property 5 is kind of trivial. The annihilator of the zero subspace is x star, and the annihilator of x is 0. This is immediate from the definition. And dually, the preannihilator of 0 in x star is x, and the preannihilator of x star is 0. So I'd like to stress that this property, and this property are trivial. But this one is trivial only modulo the Hahn-Banach theorem. So essentially, this equality states that if we have a vector such that all linear functionals, all bounded linear functionals vanish at this vector, then the vector is 0. So this is immediate from the Hahn-Banach theorem. Property 7 is also very easy. If we have two subsets of x, M1 and M2, and M1 is contained in M2, then the annihilator of M2 is contained in the annihilator of M1. This is immediate from the definition. And similarly, if we have two subsets of the dual, N1 and N2, and N1 is contained in N2, then the preannihilator of N2 is contained in the preannihilator of N1. Property 9, if we take, again, any subset M in X, we can do the following. We can first take the annihilator, and this will be a subspace in the dual, but then we can again take the preannihilator. and this will be a subspace in X. And clearly, the resulting subspace, the pre-annihilator of the annihilator, contains M. But since the right-hand side is a closed vector subspace, it also contains the closure of the linear span. Closure of the linear span of M is contained in the pre-annihilator of the annihilator. And essentially for the same reason, if we start with a subset in the dual, N, then the closure of the linear span of N is contained in the annihilator of the pre-annihilator. So first we take the pre-annihilator, and then we apply the annihilator. And we have this inclusion. Okay, so if we look once again at all these properties, we can easily see that they resemble similar properties of orthogonal complements. And let's also recall that in the case of orthogonal complements, this inclusion and this inclusion are actually equalities. So it's natural to ask, are they equalities in the general case? And it turns out that, that this inclusion is indeed an equality. We have the following result, the following theorem, the so-called the double annihilator theorem. It states that for each subset M in X, we have the following equality. The closure of the linear span of M is equal to the pre-annihilator of the annihilator of M. Well, the result is important, but the proof is very easy, because this is just an immediate consequence of the Hahn-Banach theorem. Namely, well, we already know that this subspace is contained in this one, so we have to prove the opposite conclusion. Okay, suppose that X is an element in X, and this element does not belong to the closure of the linear span of M. So we want to show that X does not belong to this subspace. So let's recall the Hahn-Banach theorem, or more exactly, the one of the corollaries of the Hahn-Banach theorem, which roughly states that closed vector subspaces can be separated from vectors in our space, in the sense that for each closed vector subspace, and for each vector which is not in this subspace, we can always find the linear functional, a bounded linear functional, which is 0 at this subspace, but which is not 0 at this vector. Well, we proved this some time ago, and if we apply this result, we see that there is a bounded linear functional, f on X, such that f vanishes at this subspace, and f doesn't vanish at X. Well, now this property means exactly that f sits in the annihilator of this subspace. So in particular, f belongs to the annihilator of M. But if we now look here, we see that f doesn't vanish at X, and so X does not belong to the pre-annihilator of the annihilator. And that's it. So this proves that these two subspaces are actually the same. Okay, let's now look at some corollaries of this result. Corollary 1. If X is a reflexive Banach space, Banach space, then for each subset N of the dual, the closure of the linear span of n is equal to the annihilator of the pre-annihilator of n. Well, this follows from the fact that in the case of reflexive Banach spaces, the annihilators and the pre-annihilators are essentially equivalent objects. But if X is not reflexive, then the result fails. And this is a useful exercise for you. Corollary 1 fails for non-reflexive spaces. Actually, this is one of the exercises in our next exercise sheet. Corollary 2 is a useful density criterion for vector subspaces of a normed space. So suppose that x0 is a vector subspace in X. Again, X is a normed space. X is a normed space. X0 is a vector subspace of X, and Y0 is a vector subspace of the dual. Then, first of all, I claim that X0 is dense. X0 is dense in X, if and only if the annihilator of X0 is trivial. Well, why is it so? The left to right implication is clear. If X0 is dense, then the annihilator of X0 is the same as the annihilator of X, but this is 0. And the right to left implication follows from the double annihilator theorem, because if we apply this to X0, we see that the closure of X0 is the pre-annihilator of this. But the pre-annihilator of this, the pre-annihilator of 0, is X. So this condition implies that the closure of X0 is X. So it is dense in X. Part 2, if we know that Y0 is dense, if Y0 is dense in X star, then the pre-annihilator of Y0 is trivial. This is also immediate from the definition, or rather from proposition 1, because the pre-annihilator of Y0 is the pre-annihilator of X star by density. And part 3 is if X is reflexive, then this statement can be reversed. If X is a reflexive Banach space, then Y0 is dense in X star, if and only if the pre-annihilator of Y0 is trivial. And this readily follows from corollary 1. And again, I don't have I have no space to write this explicitly, but again, the same exercise applies to part 3. So if X is not reflexive, then this implication fails. More exactly, the right to left implication fails. Another useful corollary of the double annihilator theorem is the following result about bounded linear operators. So roughly this result relates some properties of an operator with properties of the dual operator. Well, suppose that x and y are normed spaces, and T is a bounded linear operator from x to y. And first of all, I claim that the kernel of T star equals the annihilator of the image of T. Second, the closure of the image of T is equal to the pre-annihilator of the kernel of T star. Property 3 is somewhat dual to property 1, namely the kernel of T is equal to the pre-annihilator of the image of T star. Property 4 is not exactly the dual of 2, because the exact analog of the dual of 2 fails. And what is true is the following implication, the following inclusion. The closure of the image of T star is contained in the annihilator of the kernel of T. So in the general case, we cannot claim that they are the same. But they are the same if the space X is reflexive. If X is reflexive, then the closure of the image of T star is exactly the annihilator of the kernel of T. Part 1 is almost immediate from the definition of the annihilator, namely f sits in the kernel of T star if and only if T star of f is 0. But what is T star of f? T star of f is f composed with T. So this means that f of T of x is 0 for each x. But this means exactly that f sits in the annihilator of the image of T. Okay, to prove part 2, we look at this equality and we apply the double annihilator theorem. So we take the pre-annihilators of both parts, and we see that the pre-annihilator of this is equal to the pre-annihilator of this. But the pre-annihilator of this, by our theorem, is the closure of the image. So 2 follows from 1. And from the double annihilator theorem. Part 3 is similar to part 1, modulo the Hahn-Banach theorem. Namely, an element x sits in the kernel of T if and only if T of x is 0. But we know that an element of normed space is 0, even only if all bounded linear functionals vanish at this vector. So this is equivalent, by the Hahn-Banach theorem, this is equivalent to the property that f of T of x is 0 for each f in x in y star. But what is f of T of x? F of T of x is T star of f applied to x. So we see that this property means that all linear functionals of this form, T star of f, vanish at x. But this means exactly that x sits in the pre-annihilator of the image of T star. And that's it. So this proves equality 3. Property 4 follows from 3. Because, well, we know that the closure of any subspace is contained in the annihilator of the preannihilator. So the closure of the image is contained in the annihilator of the kernel of T. And finally, property 5 again follows from 3 and from corollary 1. So for reflective spaces, we have this equality, and if we apply this to our situation, we get this. This follows from 3 and from corollary 1. And again, once again, I'd like to stress that, again, the same exercise applies. So if X is not reflexive, then in general, this inclusion can be proper. Okay. Okay, another related result is the following theorem, which relates, again, it relates operators with their duals, and roughly it states that an operator between Banach spaces is an isomorphism if and only if the dual operator is an isomorphism. So suppose that X and Y are Banach spaces. Or actually we need only the completeness of X. So let's suppose that X is a Banach space. X is a Banach space. And Y is an ordered space. And suppose that T is a bounded linear operator from X to Y. I claim that T is a topological isomorphism if and only if the dual operator T star is a topological isomorphism. And similarly, T is an isometric isomorphism. T is an isometric isomorphism if and only if the dual operator T star is an isometric isomorphism. Well, actually, I announced this result some time ago when we began to discuss dual operators. We proved, this was a simple observation, that the left to right implications hold. So if T is a topological isomorphism, then so is T star. And if T is an isometric isomorphism, then so is T star. And this is very easy. But what is much more interesting what is much more interesting is that in the case of Banach spaces, the converse is also true. So let's prove part 1. Actually, the proof of part 2 is almost identical. Suppose that T star is a topological isomorphism. So of course I prove the right to left implication, because the left to right implication is trivial. Suppose that T star is a topological isomorphism. Then of course this implies that the dual operator, that is now which is T double star, which acts from X double star to Y double star, is also a topological isomorphism. Well, let's now identify canonically X with a subspace of the bidual and Y with the subspace of the bidual. So what do we know? We know that T is then just the restriction of T double star to X. So T is the restriction of T double star to X. And it's clear that the restriction of a topologically injective operator is also topologically injective, because topologically injective means bounded below, for example. So T is topologically injective. Okay, but what can we now say about the image of T? It seems that I'm the only participant of this Zoom conference. Well, okay, anyway. So T is topologically injective. And this implies in particular that the image of T is topologically isomorphic to X. But X is a Banach space, it is complete. And we know that the completeness is a linear topological invariant. So this implies that the image of T is complete. The completeness is preserved under topological isomorphisms of normed spaces. And this implies that the image of T is closed. The image of T is closed in Y. Okay, but on the other hand, T star is a topological isomorphism. So in particular, this implies that the kernel of T star is trivial. On the other hand, the kernel of T star is trivial. And we know that if we look here, this implies that the image of T is dense. So the annihilator of the image of T is trivial. This follows from corollary 3. But now, corollary 2, if we look here, we see that since this is 0, this means exactly that the image of T is dense. The image of T is dense in Y. So we see that the image of T is closed and the image of T is dense. This means precisely that the image of T is Y, so T is surjective. And this completes the proof of part 1. So T is topologically injective and surjective, so it is a topological isomorphism. And the proof of part 2 is absolutely identical to part 1. We just replace the word topological by the word isometric. And that's it. And here, topologically injective, instead of topologically injective, we say that T is an isometry. So T double star is an isometric isomorphism, and since T is the restriction of T double star, this implies that T is an isometry. This is the only difference between the proofs of part 1 and part 2. Just in case, I'll try to restart the Zoom conference in case if some of you have questions. Okay, probably for completeness of this picture, let's also formulate a very easy corollary of corollary 3. This will be corollary 4. Corollary 4. Again, x and y are normed spaces. And T is a bounded linear operator from x to y. Then I claim that T star is injective if and only if the image of T is dense in Y. Actually, we have already used this, this equivalence in the proof of this result of this theorem. Well, indeed, why is it so? We'll look at corollary 3. T star is injective if and only if the annihilator of the image of T is trivial, but the annihilator of the image of T is trivial if and only if the image of T is dense by corollary 2. Well, if we now know that the image of T star is dense in Y star, then this implies that the kernel of T, this implies that T is injective. T is injective. Again, this follows from corollary 3, because if we look at part 4 of this corollary, we see that the image, if the image of T star is dense, then the annihilator of the kernel is equal to x star, and so but it's better to look at property 3. So if the image of T star is dense, then property 3 implies that the pre-annihilator of the image of T star is 0, and so the kernel of T is 0. So T is injective. So this follows from part 3 of corollary 3. And finally, if we assume that x is reflexive, if x is reflexive, then we have a statement which is completely dual to 1. That is, T is injective. T is injective if and only if the image of T star is dense in X star. In X star. Oh, sorry. Here we have X star, of course. T star acts from Y star to X star. And this follows from part 5 of corollary 3. Okay, so basically that's all I wanted to tell you about duality, about dual spaces and dual operators between normed spaces. Let's now come back to the so-called fundamental principles of functional analysis. Actually, there are three basic principles of functional analysis. And the first one is the Hahn-Banach theorem, which we already know about. So the first basic principle is the Hahn-Banach theorem. The second basic principle is the so-called uniform boundedness principle. Boundedness. Or the so-called Banach-Steinhaus theorem. And the third one is the open mapping theorem due to Banach. So we already know about the Hahn-Banach theorem, and our next goal for the rest of today's lecture and for the next lecture is to prove the remaining principles, the uniform boundedness principle and the open mapping theorem. So before we discuss principles 2 and 3, we need to make a preliminary step and to discuss barrels in norm spaces. Barrels in, or more precisely, barrels in Banach spaces. Let's give some geometric definitions. So suppose that X is a vector space. This is just a vector space. At this point, I don't assume that it's a norm space. Just a vector space, as usual, over the field of real numbers or over the field of complex numbers. And we give the following definition. Suppose that we have a set B in X. And we say that B is, definition 1, B is absorbing. In Russian, поглощающее. If it satisfies the following condition, for each element X in X, there is a positive constant C such that X belongs to lambda B whenever the absolute value of lambda is greater than or equal to C. So geometrically, this means that B is absorbing. That is, it absorbs an arbitrary element after blowing it up. Property 2, we say that B is circled or balanced in Russian, circled is закругленное. Balanced — это уравновешенное. So usually circled and balanced are synonyms. So we say that B is circled or balanced if it is stable under multiplication by numbers of modulus less than or equal to 1. for each x and for each lambda, such that the absolute value of lambda is less than or equal to 1, lambda x also belongs to B. If our base field is the field of real numbers, then it's better to say balanced, because this means that it is stable under multiplication by numbers which are between -1 and 1. So it is balanced in a sense. And in the case of complex numbers, it's better to say circled, because, well, numbers of this form, they form a closed disk on the complex plane. Okay, and definition 3, we say that B is absolutely convex, if for each x and y in B, and for each lambda and mu in K, such that lambda and mu satisfy the following inequality, we have the following combination, lambda x plus mu y, belongs to the same set B. If we look at the definition of an absolutely convex set, we see that it looks similar to the definition of a convex set, because, well, B is convex if and only if this property holds whenever lambda and mu are positive, and their sum is exactly 1. But here we require a little bit more, and in fact, the relation between convexity and absolute convexity is given by the following exercise. B is absolutely convex, if and only if it is convex and circled. Convex and circled. And one more exercise. If we assume that B is circled, if B is circled, then it is absorbing. If and only if the following equality holds. So we take the union of lambda B over all positive lambda. So the point is that if we consider only circled sets, then the definition of an absorbing set can be simplified like this. So actually, this follows from the fact that if X belongs to CB for some positive C, then it automatically belongs to lambda B whenever lambda satisfies this condition. And actually, it's enough to consider only natural lambda here. This is an equivalent condition. Okay, so far, all these definitions are purely geometric. They make sense for any vector space. Now let's suppose that X is a normed space. So now let X be an ordered space. And we give the following definition. We say that a subset B of X is a barrel. That is бочка in Russian. if it is closed, absorbing, and absolutely convex. And here's a typical example of a barrel. The closed ball centered at 0 of any positive radius is clearly a barrel. We now have the following important result, the so-called barrel lemma. Lemma о бочке. So the barrel lemma states that if X is a Banach space, then this example is actually typical in the sense that each barrel contains such a ball. Or in other words, each barrel contains a neighborhood of 0. Each barrel in a Banach space contains a neighborhood of 0. Okay, let's now prove this result. The proof is a nice application of Bayer's category theorem. Namely, so suppose that X is a Banach space and B is a barrel in X. So in particular, we see that B is absorbing. So we can write the following inequality. Also, B is closed. By assumption, B is closed. And since the multiplication by a positive number is a homeomorphism of X onto itself, we see that NB is also closed. And now we apply Bayer's theorem. Which states that if I have a complete metric space, then we can never represent X as a countable union of nowhere dense subsets. Well, here X is a countable union. So this implies that some of them is not nowhere dense. There is N such that NB is not nowhere dense. And what does it mean? Well, since NB is closed, this means that, NB has a non-empty interior. Such that the interior of NB is non-empty. Well, again, the multiplication by n is a homeomorphism of X onto itself. So if the interior of NB is non-empty, this implies actually that the interior of B is non-empty. Well, this is not exactly the case what we wanted to prove. We wanted to prove that B is a neighborhood, contains a neighborhood of 0. That is, that 0 is in the interior of B. Well, to prove this, we take any element in this interior. Let X be an element in the interior of B. This clearly implies that 0 belongs to the interior of B minus X. Because the translation by X is a homeomorphism of X onto itself. Well, B minus X is contained in B minus B. b minus b is actually equal to b plus b, because b is balanced or circled. And b plus b is nothing but 2b. And this is true because b is convex. So we see that 0 belongs to the interior of 2b. But again, the multiplication by 2 is homomorphism. And so we conclude that 0 belongs to the interior of b. And this completes the proof. So this means exactly that b contains a neighborhood of 0. Okay, so this is the barrel lemma. We will see soon that this lemma is very useful because we will use it actually at least twice. First in the proof of the uniform boundedness principle, and later in the proof of the open mapping theorem. Okay, so now we are ready to discuss the uniform boundedness principle. First of all, let's give the following definition. Suppose that x and y are normed spaces. And suppose that M is a subset in the space of bounded linear operators from x to y. Then we say that M is pointwise bounded. M is pointwise bounded if for each element x in x, the following set, T of x, where T runs over M, is bounded in y. Or equivalently, this can be also written as follows. For each x in x, the following supremum, where T runs over M, is finite. It's easy to observe that if M is norm-bounded, that is bounded with respect to the canonical norm on the space of operators, then it is pointwise bounded. This is a simple observation. Well, indeed, if M is bounded, then for each x in x, we can look at the supremum. So we want to show that it is finite. But the norm of T of x is less than or equal to the norm of T multiplied by the norm of x. And the norms of our operators from M are bounded by a constant, namely by the supremum of the norms of T, where T runs over M. So this is finite by assumption, and so this is also finite. So if M is bounded in the usual sense, then it is pointwise bounded. The uniform boundedness principle says that if X is a Banach space, then these two properties, bounded and pointwise bounded, are equivalent. So if X is a Banach space, Y is a normed space, then each pointwise bounded subset in B of xy is bounded. This theorem is essentially due to Banach-Einstein-Haus. But strictly speaking, the result was a little bit different. And this final statement is probably due to Stanislav Sachs. And the proof that I'm going to present is also due to Sachs. But actually, this result is, if we look at history, is due to many people. So, strictly speaking, it should be attributed to Helly, Banach, Hahn, Steinhaus, and Sachs. Okay, so to prove this result, we look at the following set. Let's denote by B the intersection of the pre-images of the closed unit ball in Y, where we take the intersection over all operators T in M. Well, this is a subset in X. I claim that B is a barrel. Well, first of all, it's more or less clear that B is absolutely convex and closed. B is absolutely convex and closed. Well, it's absolutely convex because, well, the closed unit ball is absolutely convex. And it's almost immediate from the definition that the pre-image of an absolutely convex set under a linear map is also absolutely convex. And also it's clear from the definition that the intersection of any family of absolutely convex sets is also absolutely convex. So B is absolutely convex, and since this is the closed unit ball, the pre-image of a closed set is closed, and the intersection of closed sets is also closed. So B is closed. So to show that B is a barrel, we have to prove that B is absorbing. Okay, let's take an element little x in our space. Well, we know that M is pointwise bounded. M is pointwise bounded. So this implies that since M is pointwise bounded, there is a constant C, positive constant C, such that the norm of T of x is less than or equal to C, and this holds for each T in M. If we now divide this by C, we see that x divided by C sits in the preimage of the closed unit ball. X over C sits in the preimage of B1, in the preimage of the closed unit ball, and this holds for each T and M. In other words, this means that x over C belongs to B, and this is equivalent to the fact that X belongs to C multiplied by B. Okay, so since X was an arbitrary element, this implies that B is absorbing. Well, actually, I am cheating a little bit because here I am using not the original definition of an absorbing set, but rather I'm using this exercise. Actually, I have proved this formula. And this exercise implies that B is absorbing. Okay, so B is absolutely convex, closed, and absorbing. So it's a barrel. B is a barrel. Now we apply the barrel lemma. And we conclude that B contains a neighborhood of 0. So there is a positive epsilon such that the ball, the closed ball of radius epsilon, is contained in B. But if we now look at the definition of B, we see that each operator T from M takes this ball of radius epsilon to the ball of radius 1. For each T in M, we have the following inclusion. Or equivalently, if we divide by the epsilon, we see that the image of the unit ball is contained in the ball of radius 1 over epsilon. But this inclusion means precisely that the norm of T is less than or equal to 1 over epsilon. And this holds for each T in M. But this means that M is bounded. And this completes the proof. Okay, let's now look at some corollaries of the uniform boundedness principle. Corollary 1 is just a special case, a useful special case, which corresponds to the situation where Y, the second space, Y is the base field. If X is a norm, X is a Banach space, and M is a subset in the dual, then M is bounded if and only if for each X the following supremum is finite. Corollary 2 is about subsets in X itself. Moreover, it doesn't require the completeness of X. Suppose that X is a normed space and M is a subset in X. I claim that M is bounded if and only if for each F in x star, for each bounded linear functional on x, the following supremum is finite, whereas the supremum is taken over M. So in other words, this means that each bounded linear functional takes M to a bounded subset of the base field. Well, why is it so? To prove corollary 2, we consider the canonical embedding of x into the bidual and apply corollary 1. We apply corollary 1 to the canonical image of M in the bidual, where as usual Ix denotes the canonical embedding. Well, indeed, corollary 1 applies because x double star is the dual of x star, and x star is always a Banach space. So x star is a Banach space. This set sits in the dual of x star, and we formally apply corollary 1 to this set, and we conclude that this set is bounded. But since Ix is in isometry, we see that M is also bounded. The next result, the next theorem is formally, it looks stronger than the uniform boundedness principle, but actually it is equivalent to the uniform boundedness principle. For convenience, let it be theorem 1, and this is theorem 2. So suppose that X is a Banach space, and Y is a normed space. And M is a subset in the space of bounded linear operators from X to Y. Then M is bounded if and only if for each F in Y star and for each X in X, the following supremum F of T of X, where T runs over M, is finite. Well, formally this looks stronger than theorem 1 because, well, if M is pointwise bounded, then the supremum is also finite. But in fact, theorem 2 and theorem 1 are equivalent. To obtain theorem 2, we just combine corollary 2 and theorem 1. First of all, we consider the set T of M, the set T of X, where T runs over M. So we look at where is this set? We apply corollary 2 to this set. We apply corollary 2 to this set, and we see that this set is bounded. That is, M is pointwise bounded. And then we apply theorem 1 and conclude that M is bounded. Okay, it's time to finish. So that's all for today. At the next lecture, we discuss the open mapping theorem, which is also very important, and which is the third basic principle of functional analysis. And then we begin to discuss elementary spectral theory, some elementary effects from the spectral theory of linear operators. Thank you.